Today we are going to prove Cauchy-Schwarz equation. So first thing we need to know is what is the inner product in our case. So we are talking about finite dimensional cases. For example, consider all vectors or elements in the Rn like this. And we define inner product as if x and y in Rn, and for example writing as x as x1, x2, etc. xn. So we define the inner product as x, y, and sum up all their indexes up to n. So the claim, let me write in a red color, claim. The sum of this right hand side is less than or equal to, just wait for me, their what you say length, and this is scalar product. So and if I need to define what is this absolute value is, x is defined as square root of sum up all indexes square. So we are done. Now what about the proof? So I have a clever, or in the way you like to hear, is a bit non-standard proof. So hear me out. So first we have two cases. First case, if x and y linearly dependent, so it means that x or y is scalarly dependent on other variable or other element. So for some lambda in the scalar field, which is r in that case. So then we are done, because then y is, remember the definition, y and lambda x1, etc. So just write this left hand side. X I y I in that way. So you just distribute this lambda to all x's and the right. So we have from 1 to n xi's and lambda xi's. So it is left hand side. So what about their scalar product of their lengths? So x, y is square root of sum. Just remember this definition. xi square product, square root of likewise lambda square x square. Now just distribute this square root one another and write this as square root. And before that we can see, no, it's a bit easier than that. Just take out its lambda and we have 2 square root. So it is the sum of the indexes squared itself. So we have lambda and sum of this. You remember that this is just a real number, so we can take it into absolute value because it should be positive. So I from 1 x squared. So you see that if you take this lambda out, you get the same equation. So we are done in the first case. What about second case? I know I'm sorry about the length of this first case because it is a kind of trivial, but I needed to expand the whole equation. Anyway, for the second case, assume that it is not the case. So we have y minus lambda x not 0. So you know see the following. So its absolute value square is bigger than 0, which is obvious. We don't know if it is a negative or positive, but we take its absolute value and take square and write it down openly. So we have in the coordinate wise y1 minus lambda x1. Yeah, and sorry, and the second coordinate is 1 y2 minus lambda x2, etc. until yn minus lambda x n. So how do you write this in the inner product ways, or this definition in terms of this definition? So we got, and we have square root there. Sum of I from 1 lambda xi squares. We have absolute value and then square root, square of it. So you know the absolute value and okay, let me write it again. We have this one. Now just open this expansion. So we got 1 from n and yi square minus 2 lambdas yi xi plus lambda square xi square. So now open this again in terms of lambdas, so you get the following equation. So it's like a constant, the sum. You understand in a moment what I mean by that. So it is lambda squares coefficient plus, I'm just expanding this sum. So what about the lambda's coefficient? It is this lambda plus the constant coefficient in terms of the lambda. So we have just the sum I1 from n to n y square. So what we began with is that the whole equation is bigger than 0. So remember the second degree polynomials, if you have no root in the equation, polynomial root, so you know that the discriminant is bigger than, it is less than 0. So I'm just going to write the discriminant because the whole equation in terms of now in the lambdas, it's lambda's coefficient, and this is constant coefficient in lambda, of course. So the discriminant in lambdas is b square, which is I'm just write the same thing. Okay, from 1 xi's yi's square, b square minus 4a xi square, and c, which is this one minus I. So it should be what? It should be less than 0. So if we were to write this equation more clear way, so we have just reduced this force. Okay, I'm just going to write again for n, sorry, I from x square minus 4. You see, we are getting to desired equation here in a discriminant way, so which is less than 0, or we can put this sign here, so, and reduce these fours, fours. So what we, and then we can take the square roots, so, and then we have absolute value of this left hand side, and we have square roots all over again. 1xi square, square product of, this one. But we define this as a absolute value of x vector of x, and this is absolute value of x, y vector, which they are in the field of Rn. Now, and we know that this is just no, we define like this, no reduction here. So we get the desired results. The sum of this product is less than or equal to these two scalar products. We've proved the first case. Indeed, if they are linearly dependent, the equality holds. So in the other case, we prove that the strict inequality holds if they are not linearly dependent. So moreover, we can say that there is equality if and only if the x and y are linearly dependent.